Every year, our humid Malaysian climate and dense urban areas invite a familiar, dangerous faux dengue fever. But if you look closely at the raw mortality data from 2008 to 2017, you don't see a neat pattern. You see unpredictable spikes, devastating dips, and a tragic peak in 2015, with 336 lives lost. As data analysts and mathematicians, our story begins right here. We asked ourselves, can we find a mathematical trend line hidden beneath this real-world noise? Can we build a model to map this chaos? Before we dive deeper in this analysis, let us get to know the team members in this project. Firstly, as the leader of the group, we have Naeem, and then Aedlina and Siaswain as the representative members. Without further ado, let us know the main objective of this project is to implement the best fit curve and least square solution on the topic, to construct and evaluate data using the quadratic model, and to quantify the accuracy of using the model by calculating the least square error vector and its corresponding magnitude. To do that, we set up our baseline equation Ax nor B, where matrix A represents the timeline of years, vector B holds our actual dengue death counts, and X contains our unknown model coefficients. But when we run the numbers and apply elementary row operations, ERO, to the augmented matrix, we will get a false statement. The math shouted back a contradiction where 0 equals a non-zero number. Thus, the system was inconsistent. In the real world, a perfect mathematical curve that passes through every single chaotic data point simply does not exist. So, our story took another step. We stopped hunting for an exact solution and instead looked for the best possible approximation. We shifted to the normal system. By projecting our data into the system, we minimized our error vector magnitude to compare between three distinct mathematical models. This is the data collected from the National Dengue Mission Room, CPRC, of the Ministry of Health Malaysia in a span of 10 years. To find the ultimate best fit curve, we let three distinct polynomial models compete against each other. Our first contender was the basic linear model, y equals to a plus bx. While it gave us a steady trajectory, it was far too rigid to adapt to the historical swings of the virus. When we calculated its error vector magnitude, it scored a massive 360.0839, which was our highest error of the study. The following shows the linear graph of observed data against the year and the error vector against the year. Moving on to the next one, the quadratic model. For this model, we looked for each step precisely. Firstly, checking its inconsistency by using ERO. Next, transferring it to the system y equals to a plus bx plus cx square, and then to ax equals to b matrix form. Then we apply the normal system to gain the values for a, b, and c. Lastly, we calculated the error vector and its magnitude. The following shows the quadratic graph of observed data against the year and the error vector against the year. To elevate our analytical accuracy, we stepped out of manual calculation and integrated our digital skills using Maple software to construct and evaluate this model. Maple smoothly processed the heavy matrix operations for our quadratic trend line. The results were a massive improvement. The error vector magnitude plummeted down to 217.2998. The quadratic curve was capturing the curve of the epidemic far better than a straight line ever could. But we didn't stop there. We pushed the boundary further by introducing our final competitor, the cubic model. With an extra degree of polynomial freedom, this curve possessed the flexibility to mirror both the early dips and the massive 2015 spike in the data. When we pulled the final error calculations, The cubic model achieved an error magnitude of just 168.9439. The following shows the cubic graph of observed data against the year and the error vector against the year. In the end, our mathematical battle clearly demonstrated a core principle of linear algebra 2. As the degree of the polynomial model increases, the approximation error consistently decreases. By comparing the metrics, our story crowns the cubic model as the superior, most accurate representation of dengue mortality behavior over the 10-year span. All in all, through the power of least squares and digital tools like Maple, we can transform chaotic raw public health numbers into clear, actionable data stories. Thank you, and please be aware of dengue fever.